This video will be the last lesson in the module on graphs. This is lesson 8 in module 6, and the topic of this video is graph coloring. So the figure that you see here is a map of what they're calling in the textbook Euler Island, and it shows that there are 7 towns on the island, 1, 2, 3, 4, 5, 6, and 7. If we suppose that a cartographer must produce a colored map in which no 2 towns that share a boundary have the same color, and to keep costs down, she wants to minimize the number of different colors that appear on the map, how many colors would be sufficient? So for this map, the answer is 3, and you can see one example of a 3 coloring that has been chosen here. It might not be obvious that this problem is related to graphs, but we've talked already about how we can represent maps using graphs. We could represent a map with a graph as a graph where the vertices are the countries, and if the vertices are connected between an edge, then that would indicate that 2 countries share a border. Then this would correspond to the graph coloring problem. So we have here the definition of a graph coloring. Given an undirected graph G, we want to find a coloring function, f, from the vertex set into a set of colors, which we're going to denote capital H, such that for every edge in the vertex, or in the edge set, the terminal point, the terminal vertex, and the initial vertex of the edge will have different colors. So if 2 vertices are connected by an edge, then they will have different colors, and we want to find such a function such that H, the set of colors, has the smallest possible cardinality. The cardinality of H, the smallest number, is called the chromatic number of the graph, and we'll denote the chromatic number with the Greek letter chi, so this is chi of the graph G. A coloring function onto an n-element set is called an n-coloring. And in terms of the general problem, the graph above, the chromatic number of Euler Island would be 3. So in order to show that no more than 3 colors are needed, we just needed to find one 3 coloring. And here is a 3 coloring. We could say f of 1 is equal to f of 4 is equal to f of 6 is equal to blue. We can say f of 3 is equal to f of 5 is equal to f of 7 is equal to white. And f of 2 is red. This is a 3 coloring. So we've showed that 3 is definitely enough. Then the next question might be, well, could I do this with fewer colors than 3? Could I find a graph coloring with 2 colors? And if you look at this graph for a few minutes, which I encourage you to do, pause the video and play around with it, you will find that it is impossible. So for this graph, we need 3 colors, so the chromatic number is 3. Also, the coloring of the graph is not unique. There could be many different ways to assign this function. Not only different colors, but also just assigning different parts of the graph to different colors. Now, in the mid-19th century, it became clear to people who were studying these things that a typical planar graph will have a chromatic number of no more than 4. So at that point it was a conjecture, the 4-color conjecture, that a planar graph would have a chromatic number of no more than 4. It took almost 100 years to prove this seemingly simple conjecture, but it was proved in 1976. So we have now the 4-color theorem. It is a fact that if G is a planar graph, then its chromatic number is less than or equal to 4. However, for the purpose of this class, we don't know the proper mathematics. You actually end up needing some pretty advanced mathematics to prove the theorem, so it's beyond the scope of this class. However, we could easily understand the proof of the 5-color theorem that says if G is a planar graph, then its chromatic number is less than or equal to 5. So 5 will not be a sharp upper bound for this chromatic number because, as we said, it's subsequently been proven that 4 is an upper bound for the chromatic number. But 5 is an upper bound, and that at least gives us something to work with, and this proof is understandable to students at our level. So I would encourage you to read through this proof. It's a proof by induction on the number of vertices. You should be able to understand what's going on. But I am going to skip over the proof for now because it's not required that you understand the proof or be able to recreate the proof. You should simply know the 4-color theorem and the 5-color theorem, that the chromatic number of a planar graph is less than or equal to 4. So this is more of the proof. We have another definition here, which is the definition of a bipartite graph. And I know we have seen bipartite graphs before, but we're going to need this definition, so we'll just remind ourselves really quick. A bipartite graph is a graph that has a 2-coloring. The definition that we already knew is that a bipartite graph is a graph whose vertices can be partitioned into 2 non-empty subsets so that no edge connects vertices from the same subset. So we saw an example in the previous lecture, which was the utilities problem, gas, electric, water, and we need to connect A to gas, electric, and water. We need to connect B to gas, electric, and water, and we need to connect C to gas, electric, and water. But there are no connections between A, B, and C themselves, and there are no connections between gas, electric, and water. And this was the complete bipartite graph K33. So this is the definition that we knew of a bipartite graph, and now we're going to add to that the fact that a bipartite graph will have a 2-coloring. What we would like to assume is that these 3 vertices can all be given 1 color, and these 3 vertices can all be given the other color. So that is the first example of a bipartite graph that is given here is the 3 utilities problem, which we already know. Another example is that the n cube for n greater than or equal to 1 is bipartite. So we know from a previous lecture that in the n cube, 2 vertices would be connected if they were represented by strings whose positions only varied in at least 2 So another example of a bipartite graph is the n cube, which we saw in a previous lecture. So 1 coloring would be to color all of the strings with an even number of 1s red and all of the strings with an odd number of 1s blue. Then by the definition of the n cube, 2 strings that have the same color couldn't be connected since they would need to differ in at least 2 positions. One other interesting example, let's let V be a set of 64 vertices, 1 for each square on a chessboard, and index the elements of V by, we're going to call a vertex Vij if it represents the square in the ith row and jth column of the chessboard. And we'll connect vertices in V according to whether or not you can move a knight from one square to another. So let's think about the chessboard. I'm not going to draw the full chessboard, but we'll draw a few squares, say. And let's say our chessboard is colored like so. Well, so first of all, it's clear that the chessboard is a two coloring because we just need to fill in every other square with a color. But in this case, we're thinking about the knight and the way that it can move. Say it's here. It could move to this spot by going down 2 and over 1, or this spot by going down 2 and over 1, or it can move to this spot by going down 1 and over 2, or this spot by going down 1 and over 2. So these are all the possible moves for the knight. And using the indexing, we would say that the two vertices are connected, meaning that the knight can move there if and only if these two conditions are met. So the difference between the rows plus the difference between the columns is 3, and the difference between the rows times the difference between the columns is 2. And if you think about the example I drew on the chessboard over here, you will see that all of these moves will satisfy this. And it's also fascinating because if it starts out on a green square, then it can only move to white squares. And if it started out on a white square, then it could only move to green squares. Say it was here, then my choice of moves would be here, which would be green, or here, or here. Okay, so that's just one other example of a way that we can form a bipartite graph. So how could you recognize whether a graph is bipartite? Unlike with planar graphs, there is a nice equivalent condition for a graph to be bipartite. So what is that condition? So in theorem 1.7, we see that we have no odd circuits in a bipartite graph. An undirected graph is bipartite if and only if it has no circuit of odd length. And so again, we have the proof here of this theorem, but you're not required to be able to recreate the proof. It is a proof that you can understand, so I encourage you to read through it. But I'm going to skip over it now. I just want to point out this typo here that this should be a sentence, the next vertex in the circuit. If you're having trouble reading that, you can also find it in your textbook. So then this brings us to the conclusion of the lesson. We'll have a couple of exercises. So the first exercise, you see several images of graphs, and it asks, what are the chromatic numbers of the following graphs? So how would we attack such a problem? Well, we know that if two vertices are connected, then we want them to have different colors. So I'd probably just start at a vertex, like maybe if I'm looking at graph A, I'd start at vertex 1, and I'd just give it a color, whatever I feel like. And then I want to see if I can assign blue to any other vertices, as many as possible. But I look and I see that 1 is connected to 2, 1 is connected to 3, and 1 is connected to 4, because this is in fact a complete graph, the complete graph on 4 vertices. So right away I can say, okay, well, I'm not going to be able to give any of them the color blue, so I could move on to the next color. But then I run into the same problem. If I want to make another vertex green, well, 2 is connected to 3 and 2 is connected to 4, so I'm not going to be able to do it. So I see that they're all going to have different colors. So even though this is a planar graph, it will have the maximum possible chromatic number for a planar graph of 4. Okay, let's do the same thing looking at B. So let's say I want to just start at vertex 1 and I'm going to say that it's blue. Are there any other vertices that I can make blue? Well, clearly I'm not allowed to make vertex 2 blue, but I don't see anything wrong with choosing blue for vertex 3. And I could carry on. I have to skip 4, but could I do 5? Well, I can't because unfortunately I'm back to being neighbors with 1 and 1 is blue. So 5 can't be blue because it's got an edge connecting to 1. Okay, so let's say I decide to make 5 red instead. Well, then I can't make 4 red because red is connected to 5. I have no problem with 2 though. And so then I have to just give 4 some other color. So the chromatic number is 3 for B. And in fact, I can say chi of A is 4. If I remember that A is the name of the graph, let's just call it G. For this one, and 3 for this one. Okay, what about graph C? So I'd probably proceed the same way. I'd start by looking at one vertex. I just assign a color there. And clearly if I assign a color to 1, since 1 is connected to 2, 4, and 5, none of them can have the same color as 1, but 3 could have the same color as 1. And then I could assign a color to 2, but 2 is connected to 5, so 5 can't have the same color, but 4 could have the same color. And that means I have to use a third color for 5, so the chromatic number of this graph is 3. So if I look at graph D, if I give vertex 1 a color, then I know that I need a different color for vertex 2 and a different color for vertex 5, but I should be able to apply the same color to vertex 3. Then vertex 3 is connected to vertex 4, so I'm going to need a different color for vertex 4. Let's say we choose red. Then vertex 4 is connected also to vertex 5, so it has to be a different color, but I don't see anything wrong with 2. I can make 2 red and 5 maybe green. So the chromatic number is 3. In graph E, it looks like if I make vertex 1 a color, like let's say I say that it's black, well, the only vertex that's connected to vertex 1 is vertex 8. So I'm going to move over to vertex 7 and say I'll make it black too. But the only vertex connected to 7 is 8, so I'm going to keep going. I can make 6 black and 5, and it turns out I can do this for all of them because each of them has only one edge connecting it to vertex 8 and no edges connecting to any other vertex. Vertex 8 I clearly cannot make black, however, so I'm just going to give it some other color, and then the chromatic number for this graph is 2. And lastly, lastly, graph F, proceeding the same way. I'll say maybe vertex 1 is green, but vertex 1 is connected to vertex 2, vertex 3, and vertex 4. So I'm going to have to use a different color. This is pretty similar to graph A in the fact that all of them are connected to all of the others. So eventually I'm going to find that I actually need 4 colors for this graph. This graph will have the chromatic number 4. All right. So the next exercise asks us to prove that if an undirected graph has a subgraph that is a K3, then its chromatic number is at least 3. So K3, remember, is the complete graph on 3 vertices. So if I have 3 vertices, and each of them is connected to each of the others, then what I've formed is a triangular shape. And let's say that this is a subgraph of some other graph. So some other graph is here. It's got more vertices, more edges maybe. But I know that it has at least K3 as a subgraph. Then I want to show that its chromatic number must be at least 3. Well, let's go back to the K3 that we started with, which is here. Let's say that I start at this top vertex and I say, well, I'm going to make it green. Why not? Well, clearly then I need a different color for the next vertex. It could be black. Then the third vertex is also connected to the green vertex and it's also connected to the black vertex. So clearly I need a third color. Then it says, what is the chromatic number of the complete graph on n vertices for n greater than or equal to 1? So we just kind of thought about the K3. We thought about it sitting inside of some other graph, but we were thinking about the complete graph on 3 vertices, and we found that it had a chromatic number of 3. Well, it turns out this is true, or this continues to be true for other complete graphs on n vertices. The chromatic number for K sub n is n, since every vertex is connected. Every vertex is connected to every other vertex. So each vertex needs its own color. Lastly, the question asks, what is the chromatic number of the United States? So this one I'm going to ask you to do on your own. So think about it on your own. And we talked a little bit about how we could turn a map into a graph. So for each state, we would need a vertex. So let's say that I just made Georgia this vertex, and this is Florida, Alabama, Tennessee, North Carolina, and South Carolina. Then 2 states will be connected by an edge if they share a border. So clearly, Georgia shares a border with all of these states. So this could be the thing, and then if we had like Mississippi over here, then Alabama would be connected to Mississippi, but Georgia would not. That type of thing. So you would create a graph. It would have 50 vertices and some number of edges. And just try to play around with it and see if you can determine the chromatic number of the United States. I'll go ahead and tell you the number, but I want you to try to draw the picture. I don't know if it's really a hint. Say the answer is 4. And that might seem kind of surprising because we have 50 vertices that we could color them all with 4 colors, but it is possible. So have a little fun exploring that. This is the last exercise here in this lecture, so we'll conclude the video and conclude our module on graphs.